Hello everyone and welcome to this online edition of reInvent, and thank you for tuning in for this service launch session pre-announced by Werner. I'm Adrian Hornsby. I'm Principal Technical Evangelist with AWS, focusing on architecture, resilience, and chaos engineering. So today I'm really happy and excited to be presenting to you this pre-announced service that we've been working on. It's the AWS Fault Injection Simulator. It's a fully managed chaos engineering service. And you might be wondering what is chaos engineering. You might be wondering how to use that service or how you'll be able to use that service. So don't worry, I have answers for everyone. So let's get right into it. But first, let's look at the agenda. So we'll first talk about a little bit about distributed systems and why chaos engineering, which is a relatively new discipline, emerged as a really good solution to help dealing with complexity and uncertainty of those complex systems. Now we'll go through the current challenges our customers are facing when starting their chaos engineering journey. And I'll also explain why they have asked us to build the chaos engineering service. I will, of course, take you through the different constructs supported by the service, and I will finish with a few demos so you can also see it in action. All right, let's get started. So while the benefits of distributed computing are really undeniable and they really have revolutionized IT, there are some challenges, and those challenges are related to latency, scalability, reliability, resilience, concurrency, designing the APIs, marshalling, unmarshalling data, and complexity of algorithms such as Paxos, right? And as systems are growing larger and more distributed, what is often a theoretical edge case, right, it can sometimes turn into real occurrence, right? Now, while most people really understand that distributed systems are complex, it's quite a common misunderstanding to think that this complexity only applies to applications that have hundreds or thousands of microservices for companies like the Twitter, the Facebook, Google, or Amazon. But that's, of course, not really the case. In fact, even very simple applications are complex, right? Take, for example, this simple client-server communication. There are a lot of steps involved here in having a successful completed single round trip. So first, your client puts the message onto the network delivers the message to the server validates the message, the server updates its state, then the server puts a reply on the network delivers the reply to the client needs to validate the reply and, of course, maybe update its states. And it's quite mind-boggling to consider all the different permutations of failure that can really happen in these simple distributed systems, especially over multiple requests. So imagine how it looks when there are thousands of those or millions of them. So while traditionally the way to tackle challenges has been testing, right? But for distributed system, testing is really reaching its limit. Often we only implement the test after outages have happened in production, and of course that's already too late. So testing is of course mandatory, right? So you should totally continue doing them, but it doesn't really apply well to distributed systems, and really doesn't address the complexity of production environment. Testing those tests in isolation is not really good, and very often those tests only verify in the known condition. They answer questions like, is this what we are expecting? Is the result of that function 2, 3, 4? What about all the random failures? How about the weird errors that we see on the network, like the internet? How about configuration limits and then configuration drifts? What about the unknown? And you can test something. How can you test something that you don't know really? So some things are also just really, really hard. For example, what happened in the systems where instances start and stop dynamically, and what happened if any of those instances suddenly runs out of disk space? So I'm pretty sure many of you have had this sort of outage where suddenly an instance runs out of disk space. in one way or another. I'm sure you have that. And debugging the apps that runs on, with the disk space failure looks quite something like this, so very much faster quite often. And that's a relatively common issue, that happens when there's no log rotation. So to make things more complicated, you actually can get that error, this no space left on device error, when there's still plenty of space left on the device. For example, when your file system runs out of inodes, and because you have created too many files. So while the problems of disk space failure is localized, it isn't something that you can really catch in testing, and especially in a dynamic environment. So what really happened when your instance run out of disk space? Well, if your instance doesn't have space to write its logs, most of the time it will fail fast. And that's a real issue, because by doing so, it creates something which we call a black hole. And because it failed fast, it also fools the load balancer into thinking that the instance is ready to get more requests, which of course in turn fail. And this is what is a black hole. It's something where requests are being dumped without any success. And we could have caught that earlier, of course, before they become an outage. Improvements such as log rotation, for example, monitoring the disk space, and have some alarms that tells us when there is 10% disk space left. Well, do something. And that's just a few of the improvements we could have done. Luckily, there's a practice that helps us with this kind of unknown and failures. And that's, as you probably have guessed, chaos engineering. So chaos engineering is really a process of stressing an application or production environment, stressing an application in testing or production environment by creating disruptive events, such as a server outage, API throttling, or latency. And then observe how the system responds. And then we implement our improvements. And we do that really to prove or disprove our assumptions or our system capability to handle those disruptive events. But rather than let those disruptive events happen at 3 a.m. during the weekend and in prod, we create them in a controlled environment during working hours when all our teams and engineers are ready to tackle the issues. It's also important to note that chaos engineering is not just about improving the resilience of your application. This is very critical improvement, but it's not the only one. Chaos engineering also really helps improve the performance of your application, uncover hidden issue, expose monitoring, observability, and alarm blind spots, and improve recovery time, operation skills, and a lot more. It's also very important to understand that chaos engineering is not about breaking things randomly without a purpose. Chaos engineering is really about injecting failure in a controlled environment through very well-planned experiment in order to build the confidence in the application and the tools we are using to withstand turbulent conditions. And to do that, you have to follow a well-defined scientific method that takes you from the understanding the steady state of the systems that you're dealing with, to articulating an hypothesis, running the experiment, using a fault injection, verifying the results, and finally learning from your experiments in order to improve the system. And of course, those improvements are resilience to failure, performance, monitoring, alarm, operation, etc., etc. However, while chaos engineering is really great to have option in your toolbox, our customers have told us that they feel it's really hard to get started with. And hard because currently you have to stitch different tools together, some scripts, some library here and there, that you need to cover the full spectrum of fault that you may inject in the system, from the infrastructure, the network, the application. Each have different tools to do the job, whether it's a library, an agent. Customers really don't want to install anything extra in their applications. The more things you have to install, really, the more complex it becomes to maintain. It's also difficult to ensure a safe environment in which you inject your failure. Ideally, what you want from your tool is that they also automatically stop and roll back if any alarms are setting off. You also want to integrate nicely with monitoring solutions. And finally, some failures are simply really hard to reproduce. It's important to realize that outages really rarely happen when there's only one single failure. It's often a combination of small failures happening at the same times or in sequence, and that's just really hard to reproduce. So today, I'm really excited to introduce you to this new service, the AWS Fault Injection Simulator. It's a fully managed chaos engineering service, really easy to get started with and lets you reproduce the real-world failures we're talking about, whether they are simple, like a stop instance, or more complex, like throttling APIs. AWS fully embraces the idea of the safeguards, which is a way to monitor the blast of the experiment and stop it automatically if an alarm sets off. So getting started with the service is easy. It's something that we've put a lot of effort into it since our customers have repeatedly told us it's just hard to get started. You can use the console to get familiar with the service, try things out, and then you can use the CLI to take the full advantage of the templates and integrate that with your CI/CD pipeline to do continuous verification, for example. The templates are in JSON or YAML files, as you like, and you can share them with your team. You can version control them to benefit the best practice associated with code reviews. So you can run your experiments in sequence or in parallel. The sequence are often used to test the impact of gradual degradation, like a sequence of actions that gradually increases latency or gradually increases the CPU consumption in your instances. And then you can do parallel experiments to test the impact of multiple concurrent issues, which is often the case in real-world outages. So the supported services to get started will be EC2, RDS, ECS, EKS, and of course a lot more will follow. So you can create those complex conditions that really span across a large sets of AWS services. So just to hit the nail on the head here, those faults are really happening. It's at the service control plane level, right? So an instance is actually going to be terminated. The memory is actually going to be consumed and utilized. The APIs are actually going to be throttled. So there's no faking it layer. There's no faking it with metric manipulation. So please really use extra caution when using that service. The safecards act like the automated stop button. It's a way to monitor the blast radius of an experiment and make sure that it's contained and that failure created in the experiments are rolled back if the alarms are going off. The IAM control that you can use can define what kind of fault types and what resources can be affected. Also using tag-based policies, so you can, for example, only target instances that have a tag environment and test or chaos ready, something like that. So there is an architectural diagram of the service. As you can see, you can of course use the console and the CLI, and then you can integrate with the AWS identity and access management so that you can be sure that only the authorized party can run your experiment. You can, of course, define very fine-grained controls, what type of faults are authorized and on which resources. When you create your chaos experiment from the console, Fields automatically creates a template for you, so you can reuse that template later. And once you start your experiment, Fields inject real failures on your AWS resources. So it's best practice to really have your CloudWatch alarms monitoring AWS resources and workloads and define some stop condition that will automatically stop the experiment if they change status. And finally, you'll be able to integrate your own monitoring solution by Event Bridge in order to trigger the stop condition. So to use this service, you'll only need to understand 4 components: the actions, the targets, the experiment templates, and the experiments. So let's take a look at all of that and see how we can define them. So the actions are really the fault injection actions that you execute during an experiment. They are defined using the namespace AWS, double column service name, double column action type. The actions include the fault type, the duration, the targeted resources, the timing relative to any other actions, the fault-specific parameters such as the rollback behavior or the portions of request that you want to throttle. So this is the JSON representation of an action definition. There are two different actions defined in this one. There's the stop instances and terminate instances, and each have different targets. So notice that the terminate instance is ordered to execute after the stop instance. So that's a sequential experiment execution. It's also worth noting that some actions on EC2 instances, for example, are performed through the AWS System Manager agent, the open source Amazon software that is installed by default on most Amazon Linux and Ubuntu images. You can, of course, install it on your custom instances as well. And I'll show you some integration at the end. Targets define one or more AWS resources on which you want to carry out an action. So you define the targets when you create your experiment template, and you can use the same targets for multiple actions in your experiment template. So the target includes the resource type, the resource themselves, of course, through the resource IDs, the filters, and the tags, and the selection mode, that's defines how many of those targets you want to select. For example, all of them or random selection. So this is the JSON representation of targets. And here we can see the usage of filters that target only instances that are running in one particular availability zone, US East 1A. And it's not the only filter here. You can also notice that I'm using tags to refine the selection. And I would say that using those tags is always the best practice. And in this case, only the instances which are tagged with purpose chaos ready will be targeted. It's somehow another level of safety to prevent mistakes. So the experiment template define an experiment and are used to start an experiment request. And they, of course, include the experiment template. The experiment templates include the actions, the targets, stop conditions alarm, the IAM role that you want to use, the descriptions and the tag. It looks something like that. Again, you can use JSON or YAML as you prefer. You have the name using the tags here, name, the description, the IAM role, stop condition, targets, and finally the actions you want to perform. And of course, since it's a template definition, there's no order, right? You can put them as you want. As explained earlier, you can run simple experiment like the one on the left, sequential and with very specific targets, or you can create more complex experiment, which is a mix of sequence and parallel execution with advanced filtering, for example. For both, I strongly suggest to use alarm, especially in prod, even in tests, so you get familiar with the idea of using alarm for your chaos experiment, which is really critical to fully benefit the power of that service. Finally, we have the experiments, which is really a snapshot of the experiment template when you've launched it. It's the history of execution that you get. And it adds on top of the snapshot, it adds the creation and start time, the status of your experiment, the execution ID, experiment template ID, and IAM role RN, so that you can really keep a full history of what all the experiment that you've run. Here are some of the faults we are bringing in for the service, with more in 2021. And of course, this may change, so take this with a grain of salt. It may change as we receive feedbacks from you. Now let's do a few demos so that you can see all the features in action. We'll start with a simple experiment in the console and get into more complicated experiments with the CLI. So we'll start with a start and stop experiment. So when you log into the console, you'll see this is the Fizz console, so you can start. The first thing you need really to do is to create your experiment template, and then you can describe what your experiment will be. Here's going to be a stop and start experiment. Then you can select the IAM role that you want to use for that experiment. That will be my Fizz experiment role. The documentation will help you how to create those roles. When you create your first action, the name is going to be a stop instance, right? And action type is, of course, EC2 stop instance. The duration in minute here will just put 1 minute so that you can see quickly how it goes. Then it creates a target automatically for you, you'll see, and you can of course change the target if you want, but there's an action parameter here which is start the instance at the end, which is optional, and this is restarting the instance after it's been stopped, and we've put that to true so you can see how it works. Then we create our target. Here I'm going to target a single EC2 instance. Right. You can of course select more, you can have a combination of tags and filters if you want. So let's start with one single instance. I won't put any stop condition here so that you can see, but yeah, it's just to show you how it works, and then we'll put the stop condition in the next demos so we can see the difference. Right. So let's create the experiment templates. And of course here you notice, because I didn't put a stop condition, I'm being asked, do I really want to do that? So if you get that, you probably should create a stop condition. So now we've successfully created our first experiment template. What we need to do now, so we can of course look at the different parameters, we can see the actions and targets here, but we can simply start and see what happens. So let's start. Again, we are asked if we want to tag that experiment. We need to confirm by start, yeah, we are doing destructive actions on our AWS resources, so do we really want to do that? And then you can see we've created now an experiment that is now running. So what we can go now is go and see the instances on our EC2 console, and you see our instance is already stopping. So it's going from a running state to a stopped state, and the transition state is stopping. So now the action is in pending because the state of the machine is still stopping. And then once this is executed, you can of course verify all your experiment and the targets, and now this is stops. And you see already now the instance restarts automatically because the 1 minute length of that experiment. So we stop the experiment and automatically the experiment has restarted the instance. And this is now completed, and you can verify the state of the experiment in your console. All right, so the next demo is going to be reusing that one, but adding a stop condition with alarms now, so that we can see how it behaves. So let's take that for that same template, and what we'll do is we'll simply update it, and this is a cool way to do that. But first we'll use a CloudWatch alarm. This is one that I've created early that verifies that I have network packets going on into my instance inside the US East 1. So all my fleet of instance, if there's no more network, I want an alarm to set off. So let's update now the experiment template to add this alarm there. You just simply go into the stop condition and you can start adding it. You see it's already there because it automatically pre-populates with all the alarms that I've defined in my region. And then what we'll do, we'll also update how long the stop instance lasts. So we'll put a few minutes or 3 minutes so that it doesn't go too fast, so you can see the effect of the alarm. All right, let's update that. Let's verify that our instance is now running. Yeah, so let's do, it is running, initializing, but it's good. So let's start the experiment. And let's, of course, click start because we are about to do a disruptive action on our resources. And now you see my action is pending. And we can, of course, verify again that our template is doing the right thing. Now there's a slight difference here that I have now the stop condition, so you can link directly to your CloudWatch alarms. And yeah, so my instance now is stopping, of course, so that's good. All right, so let's wait a couple of seconds so that the instance states move from stopping to stopped, and now it is fine. Yeah. So what we can go is now verify that our alarms is still okay. So let's now synthetically change that. So we can use the CLI to actually inject the tests into the alarm and setting the alarm, modifying the alarm and put it in alarm state for simply 1 minute. That will do that. And that's enough to trigger the experiment rollback. As you see now, my alarm is in alarm. My CloudWatch alarm is now off. And the experiment is rolling back. So that means it's restarting the instances. So that, stopping the experiment and rolling back. All right, and that's a really good way to deal with your experiments. And it's also updating, of course, the status of the experiment, telling you that the experiment was manually stopped. All right. So the third demo here, we're going to do some stop instance with some filters and alarms, but we'll use the classic one. Very often people should deploy their application across multiple AZ. Here I'm using 3 availability zones. So I'm going to want to stop only the instances that are in US East 1B. And to do that, I'm creating a filter, which is filtering for the US East 1B and instance states that are running. And then putting a duration of 2 minutes. So that was my template. I can take that template and create an experiment quite simply by feeding it to the CLI. Then I have the ID now of that experiment template, and you can of course go into the console and that ID will be there. You did filter instance. You can of course filter also your experiment in the console by the IDs as you wish. Verify all the time, make sure it's correct. It's better to verify twice, especially when we're going to do some fault injection. You can see here my filters, you can see the tags. All right, now let's go back into the CLI and actually start that experiment. So we take the ID of the template, we start the experiment, and then that's running. So that the state is running, so I can start going back into the console and see if my instances are actually stopping. And as you can see, yeah, all my instances that are in this availability zone now are stopping. So the filters are working as expected, which is a good thing. You can, of course, filter, look at the history of all your experiments here and filter by the ID and see what actions did you take, what target did you use, all this kind of stuff. Right, and of course now my CloudWatch alarm is back to normal as well. Right? So what we can do now is stop the experiment the same way we did previously. So let's put the CloudWatch alarm in an alarm state. Right? So you see now my network in abnormal alarm is running, and of course now the experiment is going to be rolled back, so all my instances are going to be restarted automatically. As I say, you can enable this rollback or not. If you don't want the experiment to roll back, you can put the rollback part of the targets, to false, of course. By default, it's on false, but yeah, it's good to be safe. All right, so now my instances are rerunning. And that's good. So let's move into the last demo that we have for today. And this is a CPU stress fault injection. And we'll also do a stop experiment. And for that, I'm using a template as well. And this is the integration with System Manager. So especially a part of System Manager called run command, send command here. So you need to refer to a document which implements the fault injection and will give you a bunch of documents to get started. This is a really advanced use case, so you can define your stress on the particular instance that you want to do. This is the SSM document that is being used, and there are different steps first to do the initialization and installing the dependencies, and then, of course, doing the fault injection using stress-ng. All those templates will be provided at launch. Some of them will be fully managed. It's just to show you the integration and how the service works. You can, of course, override the parameters, the default parameters of the document if you wish, by giving it the parameters at execution time on the experiment template. So let's do the same. Let's create the experiment template by giving it the file name. All right, and then it adds, of course, all the parameters that we want, you know, the last time update, all this kind of stuff. This is also the ID of the experiment template that we have. And now we, of course, want to log into the instance that we're targeting. So let's verify first that that's the right instance. So by using the EC2 metadata API, so we can see here that the instance ID is the same as in the template. Yeah, that's good. So let's use hstop so we can see the value of the CPU and the memory as we move forward and execute the experiment. Now let's just start the experiment and see how it happens. So give the template ID, and you'll see now it's going to give you all the details of the API, what is happening. Again, it's a verification that you're doing the right thing. It gives you the status of the experiment. So status is now running, the experiment started, and you can see already now the CPU in the instance is running hot. So the fault injection is happening, and we can take this ID of the experiment and stop the experiment. Now it's worth noting that not all the SSM templates can currently be stopped because some of them modify the state of some experiments. So again, with advanced chaos engineering, it's very important that you're very careful and with what you're using, okay? So just be aware about that. Some faults modify the states of some resources. So before doing anything, always test in your non-production system, get confident in the tools, be confident about all the actions, what they do and how to revert and all this kind of stuff. That will set you up for success. We will add a lot of templates and documentation so that it's going to be very easy to get started. So on that note, thank you very much for joining me for this session, and have a really wonderful end of reInvent. Oh, and I almost forgot, remember to complete the survey, please. That's really how it's really helping us to improve the conference. Thank you very much, and take care. Bye-bye.